cards. Where'd my cards go? There they are. All right. Suppose I have 5 cards, which I really do. We're going to play a game. I have 5 cards. Two of them are aces. So there's my 5 cards. Queen, ace, 8, ace, 2. So I have 5 cards to choose from. 2 of them are aces. You will select 2 cards total, but one at a time. We're going to find the probability of drawing 2 aces. So we have event A. The first card selected is an ace. And event B, the second card selected is an ace. So, who wants to draw a card? All right. What's the probability that Hannah's going to draw an ace?
2 out of 5.
2 out of 5.
20%.
Oh, she got it.
Wow.
Good job. All right, so I put it back. What's the probability that Hannah's going to draw another ace? Oh, she didn't get it. All right, let's go to the other person. What's the probability that Eric's going to draw an ace? 2 out of 5. Oh, he did it. I put it back.
Yeah, we can see the line. Another shuffle.
Oh, see, I'm going to play you. All right. So, the probability that Hannah or Eric drew an ace on their first card was 2 out of 5. Then I put the card back. Probability was still 2 out of 5. Now we're going to do it without replacement. That means that after the first card is drawn, I don't put it back. All right, what's the probability Alex is going to draw an ace on his first card? One card. One card. Oh, he didn't get it. Anybody else?
He's got a sword.
Probability, no, new
Did you
game.
not put the card back?
I put it back because it's a new game. Calvin got an ace, so I keep it out. I'm going to give it to Hannah. What's the probability Calvin can draw an ace?
So it increased his odds.
Oh, man. Usually I have at least one winner. Let's go for one more. Who else wants to draw a card?
Tyler, you should do it.
All right. What's the probability you're going to draw an ace? Nate? You got an ace. What's the probability you draw an ace?
3 out of 7.
Oh, sure, dude. Nobody won this year.
Wait, who won?
I don't remember, but usually I always have a winner in previous years. All right, so probability we get an ace on the first card, 2 out of 5. I kept it out, so the probability then changed to 1 out of 4. So we have a new definition. The probability that one event happens, given that another event is already known to have happened, is called conditional probability. So suppose that we know that event A has happened, then the probability that event B happens, given that A has happened, is denoted by the probability of B given A, and yes, that given symbol is just a straight line. So really up here, this should say the probability of B given A is 1/4, because the probability of B changed given that A happened. Molly?
What if you didn't draw an A? Would it be 2 out of 4 for the probability of B? 2 parts?
Sure. But A is the probability the first card selected is an ace. So yeah, I guess you could say it that way. I was just going for 2 aces. When Alex didn't draw an ace, I said he lost it and we were done. Any other questions? All right. Going back to our jacks and red cards. So we've already made this two-way table, so I'm going to have you guys do it again. I want you to create a two-way table that has events J, getting a jack, and event R, getting a red card. Construct your two-way table, then we'll do the probabilities together. Total? Yeah.
Oh.
That was your question. All right, so hopefully your two-way table looks similar to this. We have the probability of getting a jack, or I shouldn't say probability, excuse me, our event getting a jack, J complement, so not a jack, red, R complement, so not a red card or a black card. We have 4 total jacks. Out of 52 cards, that means 48 of them are not jacks. 26 of the cards are red, meaning 26 are not red. Out of the jacks, 2 are red, 2 are not red. So then we have 24 red cards that are not jacks, and 24 not red, not jack cards. So what's the probability of J and R? 2 out of 52,
Or 1 out of 26.
or 1 out of 26, or who knows what that decimal is. I know I got it last time in class, but oops, might help if I could actually type 2.038. And what is the probability of getting a jack? Thank you. 4 out of 52. Or 1 out of 13. Or 0.077. So then we want to find the probability that our card is red, given it was a jack. So what is the probability that our card is red, given we know it's a jack? I want you guys to think for a minute. How did you get 1/2 pounds?
Because you have 4 jacks and, I guess?
You have 4 jacks,
4 jacks, 2 of them are
2 of them are red. So if we know that our card is a jack, because that's the given condition, that means we only are looking at these 4 cards. And out of those jacks, only 2 of them are red. So we get 1/2. Does anybody, and I'm going to give you a hint here, look at these probabilities out of 52. Does anybody see how our probability here relates to the previous probabilities we had? China. Say it a little louder for me.
The numerators equal the probability of R.
So she noticed that our numerators, 2 and 4, those are the numbers we use to find our probability that our card's red, given it's a jack. And I'm going to take that one step further. We're going to use the full fraction, but because we're going to end up dividing, the 52s cancel each other out. So when you're finding a conditional probability, you're going to take the probability of the 2 events together, so red and jack, and you're going to divide by the probability of the given condition. And by the way, I didn't do this on purpose, but does it matter that I wrote R and J rather than J and R? No. They're the same thing. That's a jack and a red card. That's a red card and a jack. There's only 2 no matter how I look at it. So we know the probability of R and J, or J and R, is 2 out of 52. And then we know the probability of J is 4 out of 52. So we have a fraction divided by a fraction. So we get to think way back in our math training. When you have a fraction divided by a fraction, you flip the bottom one. And of course, I might be able to squeeze it onto the side there. So that means that I have 2 out of 52 being multiplied by 52 out of 4. because I flipped the one I'm dividing by. And then our 52s conveniently go away. And we end up with 2 out of 4. So just like Cheyenne pointed out, we end up using the numerators. So when you're working with a conditional probability, if you're given that event A has occurred, what's the probability that event B will occur? Or in notation, probability of B given A, you're going to take the probability of A and B and divide by the probability of A. You always divide by the given. So now we're going to practice using our new probability rule. Can I flip it over? Ah! I hate when I let go and it totally disappears. What, Hayden?
Oh, they said my name.
I didn't even say anything that sounded like Hayden.
Oh, my bad.
But I'm glad you're paying attention now. No response to that one. All right. So we're going to, like I said, practice using our conditional probability rule. So my example here is the Titanic. Please tell me you guys all know about the Titanic. Okay, sorry, side story. I had a student tell me they wanted to be an anthropologist so that they could teach the majority of the year and only be called out like 6 times a year. And I said, so you want to be Indiana Jones? And they looked at me. Do you guys know who Indiana Jones is? Oh, good. The student looked at me like I was crazy. I'm like, how do you not know who Indiana Jones is? Kind of made me feel old, but I'm glad that most of you know.
What's an anthropologist?
Oh.
Who's an anthropologist?
They study like the history of people, I think.
Historian.
Kind of like the study of culture and history.
Yeah.
Ah.
Thank you, Nate. I knew I wasn't right on track.
Also what I want to do.
So you want to be Indiana Jones?
Kind of. I want a minor in anthropology.
No,
He wasn't an anthropologist, he was an archaeologist.
don't they do the same thing?
No. No, he's kind of bold. He's mainly an anthropologist.
Yeah.
That's what he is, yeah. Anywho, back to the Titanic. In 1912, the luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. The two-way table gives information about adult passengers who lived and who died by class travel. So we're going to choose an adult passenger at random. So we have our table. Part A, given that the person selected was in first class, what's the probability that he or she survived? Then part B, if the person selected survived, what's the probability that he or she was a third class passenger? So first thing we need to do is get our totals. So I'm going to add on to our table a little bit. And I'm going to use my abbreviation for total, because I'm feeling lazy, so TTL. And then we have 197 plus 94 plus 151. So we have 291 who survived. Oops. Did my brain, my calculator buttons are sticking. That's not right. This is 442. Sorry. I could have sworn I hit enter, but apparently I didn't. 167, 476. So this is 765 here.
Those are your pants.
What are you stealing them for?
Leadership, I don't know. That's all that I've been told. Definition
So
of
he really is stealing. I know. Leadership. For leadership, that's all that matters, right? All right. So grand total 1207. And then I need to get my totals for first class. See, I cannot type today. I'm sorry. 319. 261. And 627. And I'm just going to double check those three actually add to 1207. Okay. So I have my totals. So A says, given the person selected was in first class, what's the probability he or she survived? So we're given they're in first class. And we want to know the probability that he or she survived. So I'm going to do the probability they survived given they were a first class passenger. And I'm just going to put first rather than first class. So our new rule tells us that I'm going to find the probability that they were in first class and survived. And then I'm going to divide by the given condition, which was that they were in first class.
So 197.
I heard the 197, and then all I heard was those things outside going round.
319.
So probability first class and survived. It's right here, 197. And that's out of the grand total, 1207. And then we're going to divide by the probability they were in first class, which is 319 out of 1207. And I showed you guys when you have a fraction, divide by a fraction. Because our denominators match, they conveniently go away. And we get 197 out of 319, like Alex said. And then we're going to change it to a decimal. 197 divided by 319, so about 0.618 if I round. 618. You guys are going to do B on your own if you haven't already. Sorry, I just noticed I'm kind of off the side there. So. No, I just want to be crystal clear about how we got it. Because technically, the probability of getting that they were in first class and survived is 197 on it, all of those stuff. feel like somewhere in there I said that died, survived, but I don't know what I'm saying. Survived. You have this one. No. I'm seeing a lot of you doing the wrong conditional probability. If the person selected survived, that's your given.
That's your denominator. Because you always divide by the given, right?
This is given.
But the wording's mean.
The wording is mean.
Yes. Can you fairly understand it? I mean, it's basically.
I wouldn't say the wording is mean.
Just my head. Basically, the actual thing about it.
Yeah. Will you go get it on the board? Writing by the probability to survive. The top stays the same. Nope.
I like the Christmas sweater.
What? Where are your words? Oh. But then I know I feel, yeah, it might help you. Words are important. I never thought you'd hear me say that. I never thought I'd say that. Oh man. I'm going to the dark side. Of what? I don't know, saying words are important.
You sound like an English teacher.
Words matter.
This is right. Hopefully.
I don't know, I can see your hands.
Why do you have to divide it by the?
We divided by the given because that's what she said.
That's good. What was your question, Hannah? I'm sorry.
Yes.
Just going like that.
Just confused.
They're my favorite.
You got the top part? Okay. I think I got the full part.
Whatever you're giving from.
What are you guys talking about?
You got 4 points?
Oh,
Yeah.
well, you are. But technically, the probability of the third class
Wait, it's not 627.
All right,
Plus,
we're looking at the probability that the passengers in third class, given they survived. So the probability that they're in third class and survived divided by the probability they survived. So third class and surviving is 151. So we have 151 out of the 1207. Now some of you asked when I was walking around, do we really have to put the 1207? Yes and no. I'm not going to be picky about it if you don't do it, but technically the probability that they were in third class and survived is a fraction. It's not 151. It's a decimal. Probabilities have to live between 0 and 1. So if you skip the step of showing the denominator, which, like I said, I'm not going to be picky about, and then the next question is, what's the probability they were in third class and survived, and you give me 151, you're going to get it wrong. So I suggest putting it just so that you get in the habit of actually finding your probabilities, but you don't have to.
what if you just pull up 151 442?
I just said that was fine, and I'm not going to be picky about it.
Oh.
Probability they survived. Now I saw a lot of you that had probability of third class down here. Our rule, formula, whatever you want to call it, for conditional probability. Probability of B given A. Notice the given is what's on the bottom of our fraction. So since this was third class, given they survived, we need to divide by the probability they survived, which is 442 out of 1207. Cheyenne then showed that you multiply by the reciprocal, the denominators cancel out, we get the 151 out of 442, or 0.342. Nate?
Should we normally round to the thousandth place?
I'm sorry, I did not hear you.
Should we normally round to the thousandth place?
Yeah.
Okay.
Any other questions? Don't worry, we're going to do some more practice with this, okay? So down below, another two-way table. And if I remember correctly, no, must have been a different two-way table. I thought I had my total wrong, but you can see my total's correct. All right, so the following two-way table describes the 595 students who responded to a school survey about eating breakfast. Suppose we select a student at random. Consider events B being they eat breakfast regularly, and M, that they're male. So we have eats breakfast regularly, 190 males said they did, 110 females said they did, so we have 300 total. Doesn't eat breakfast regularly, 130 males said that they don't, 165 females said they don't, so 295 total. That's 595 total there. 275 females responded and 320 males responded. So we want to find the probability of B given M. So what's the probability they eat breakfast regularly given they're a male? Probability of B given M. We're going to take the probability of B and M divided by the probability of M. So probability they eat breakfast and they're male. I heard quite a few of you say 190 right off the bat. And that's true. 190 males eat breakfast regularly. I am going to show my denominators. You guys do not have to. So that's the probability they eat breakfast regularly and they're male. And then what's the probability that they're male? 320 out of 595. So those 595s go away. And we get 190 out of 320. And if I change that to a decimal, we get 0.594. Now, I did add something to this question. It says, explain what this value means. You guys thought you got away from interpreting things because it was probability, huh? Never get away from interpreting things. And of course, I wasn't thinking ahead. I ain't give myself a lot of space. Not that it's a long explanation. I just have big handwriting. Let's see. I'll put it down here. So given that the student is male, we would expect that they eat breakfast regularly. Why am I struggling with that word? There we go. 59% of the time. And yes, I did get rid of the 0.4. I should have said 0.4. You guys are going to do B. Probability that the student is male given they eat breakfast regularly. And then interpret. Explain what it means. Give me a sentence. Thank you, Shelby. So the probability of male and eating breakfast stayed the same top fraction, 190 out of 595. This time you're dividing by the probability that the student eats breakfast regularly, which is the 300 total over here. So you have 190 over 595 divided by 300 over 595. The 595s cancel out. So you get 190 divided by 300 or 0.633. Then her explanation, this means that given that the person eats breakfast regularly, the probability that the person is male is 0.633. Any questions before I flip? All right. So this one says Here is the distribution of the adjusted gross income in thousands of dollars reported on individual federal income tax returns in a recent year. So at the top, we have income, and it tells us that it's in thousands. So less than 25,000, the probability is 0.431. 25,000 to 49,000, 0.248 for the probability. 50,000 to 99,000, 0.215 probability. 100,000 to 499,000, 0.1 probability. And then greater than 500,000, 0.006. So question A says, what's the probability that a randomly chosen return shows an adjusted gross income of 50,000 or more? So just to be lazy, I'm going to put 50 plus. Probability of 50 plus, 50,000 or more. So on this one, we're going to end up adding more than one of the probabilities together. So 50 to 99,000 is 0.215. 100 to 499,000, which is greater than 50,000, is 0.1. And greater than 500,000, which is also greater than 50,000, is 0.006. So we're going to add those three given probabilities together to get the probability that the income was 50,000 or more. So we get 0.321. Any questions on that one? All right, then part B says, given, given that a return shows an income of at least 50,000, what is the conditional probability that the income is at least 100,000? So we have a given statement. Given that the return shows an income of at least 50,000. What does at least mean? You guys gotta talk louder. I'm old apparently. What does at least mean? Say it louder. Greater than or equal to. So really, this means the same thing as this, right? 50,000 or more. So our given is the probability that the income is 50 plus. So we just found our denominator. Then we want to find the probability that the income is at least 100,000 or greater than or equal to 100,000. So I'm going to find the probability of 100 plus and 50 plus, and then I'm going to divide by the probability of 50 plus. Now, the 50 plus we just did in part A. We got 0.321. If your income is 100 plus and 50 plus, really what is the minimum income we're looking at there? Are we looking at a minimum of 50 or a minimum of 100? if your income's, let's say, 68,000, are you at 100 plus? No. So it's a weird statement there, but we're really only going to look at 100 plus, which is these two end probabilities in our table. I mean, technically, those ranges of incomes are 100, excuse me, 100,000 or more and 50,000 or more. It's just this one that we have to avoid because it doesn't fall in the 100,000 or more category. Say that louder.
Because it only goes to 90.
Correct. So we're going to have 0.1 plus 0.006 on top, which is 0.106. So we get 0.33. And a lot of times, that's how probability problems are set up. Especially with conditional probabilities, you'll find one of them or both separately, and then you'll have to use them together. You guys are going to do the Mac or PC one on your own. I suggest that you make a two-way table or a Venn diagram to help you out. You don't have to, though, but at least I personally found it helpful, so I suggest it. your total market. 4 in the middle. So a lot of you were able to get your table done. If you haven't yet, Cheyenne is putting the correct two-way table on the board. And then I'll give you guys another minute to figure out the probability that the question is asking you correct. Carter's gonna go put the probability on the board for us. All right, I'm gonna zoom in a little. So we have probability that the student's a graduate given their PC user. So he did probability of graduate and PC user. Now, when he made his table, he had 100 as the total. So that's why he's got like 23 out of 100, not 0.23 out of 1. But 0.23 is the same thing as 23 out of 100. So 23 out of 100 for graduate and PC user. And then you're dividing by the probability they're a PC user, which is 0.6 or 60 out of 100. The hundreds cancel out, so you're looking at 23 out of 60, which gives you 0.383. Questions? Yes, sir.
How would I do this if I wanted to do it as a Venn diagram?
I knew somebody was going to ask that question. All right, so if you were to do a Venn diagram, and as much as I sighed when you asked that, Nate, I'm glad you asked it, because some people prefer Venn diagrams. So the two main events that we're looking at for this probability is graduate and PC. So that's what I'm going to label my circles as. We have the nice statement that tells us our overlap. 23 were graduate students who said they use PCs as their primary computers. So we automatically know that centerpiece, graduate and uses a PC, is 0.23. Then if I go back and look at the other statements, 40% use Macs, which means what percent use PCs? 60. So the 0.23 plus whatever's over here need to make 60% or 0.6, which would mean I have 0.37 over here. 0.2 and 0.3 make 0.5. The 3 and the 7 make 10, so I have 0.6 there. Then my other statement says 67% are undergraduates, which means what percent are graduate students? 33%, and I already have 23 of that 33, which leaves 0.1 over there. And then to get the outside, so not a graduate and not a PC user, so an undergraduate who uses a Mac, I would do 0.1 plus 0.23 plus 0.37, which is 0.7. And I would take that away from 1, so I get 0.3 on the outside of my circles. Then if you were to do probability of graduate given PC, probability that they're a graduate and use PC is 0.23. Probability that they use PC is the 0.23 plus 0.37 or 0.6. Then you still get 0.383. Oops, sorry. There we go. Yes, sir.
Would it be possible to do a Venn diagram with our categories being math and undergraduate?
Sure.
So, yeah, how would you do that? Sorry.
No, it's okay.
I'm trying to figure it out.
It's okay.
So
You should be able to. I haven't done it myself because I went with graduate and PC,
I got
But-
stuck, so that's what I'm wondering about.
but we should be able to do it. So you chose undergraduate and math.
Yes.
Okay. So I know that 40% use the Mac. 67% are undergraduates. 23% are graduates who use PCs. So that should be on the outside. 0.23. Right? You would agree with me on that? So then that means I have what? 0.77 left for the rest. And I know that 40% are for math. And then undergraduate is 0.67. So 0.4 plus 0.67 would be 1.07. And I only have 0.77 left. So that means I'm over by 0.3, which would mean that my center has to be 0.3, where I've counted it twice. Am I making sense?
Yeah, so it's, you add the two probabilities up and then subtract the probability that neither of them happens?
Yeah.
Okay.
Well, not that neither of them happens. So I have the graduates and PC users is 0.23, which left 0.77 for my undergraduate, Mac user, and Mac user. And when I did the Mac and the undergraduate, I got 1.07. So I was over by 0.3, which would be what I end up counting twice between those two guys. Did I clarify?
Yeah, that's the part that I got stuck on. I didn't know
Okay.
how to find the shared area.
Which then would mean that I have 0.1 left here and 0.37 left there. Any other questions? All right, so don't follow the numbers on your homework sheet on this. I shouldn't say, I said that wrong. Follow the numbers on the worksheet, not on this sheet. They don't match. Follow this one. Okay?